Syzygy, episode 89, Diverting Dimorphos with Dart. And welcome back to another edition of the Syzygy podcast. My name is Chris Stewart, in the office of Dr. Emily Brunsden, who's sitting opposite me here at the table in her office. Emily, hi, how are you doing?
Hello, I'm very good.
I just tripped over that one completely, but we're just going to keep going.
It's okay, because we're in my office.
Keep going. We're in your office. It's important to point out where we are. So, Emily, today we are going to be talking about something which is potentially a little bit worrying, but I'm really hoping that by the end of today's episode, I'm going to feel much less concerned about this topic. Today, we're talking about trying to stop asteroids bashing into the Earth and killing everyone.
Yeah.
Yeah?
Ish.
And you're about to tell me that this is something that we really don't need to worry about. And even if we did, don't worry about it. We've got it sorted, right? Okay, so looking back on the sort of popular history of this idea, right, you don't have to go terribly far to find a big Hollywood blockbuster in which the scientists of the world, the astronomers, discover a big chunk of rock hurtling towards the Earth. Quick, call up the president. Get the president on the line. And the president says, you know what we need to do? We need to nuke this sucker. And what do? They send some really fit dude up in a rocket and lands on the asteroid and plants a nuclear weapon, and then at the last minute they can't get off the asteroid in time, and so the hero gets blown up with a nuclear bomb, but saves the world. That's what we're talking about, right? We're sending nuclear weapons to destroy asteroids. Yeah?
I mean, you should have gone with spoiler alert there, but in addition, my spoiler alert is no, we're not doing that at all.
Well, listen, I mean, okay, on spoiler alert, as far as films like Armageddon are concerned, if you haven't seen it by now, A, maybe don't bother, and B, what have you been doing? Like, come on. I'm not going to do a spoiler alert for a film which is that old. But we're not talking about that. Instead, we are talking about something which is a little bit more subtle. This is a mission which has just been launched. Emily, What are we talking about?
Yes, we're talking about DART, which is a NASA mission launched on the 24th of November, so just a few days ago.
Just a couple of days ago, yeah.
And the idea is to send DART to, which is, okay, I've got to tell you the acronym because it's worth it, right? The Double Asteroid Redirection Test.
Oh, okay. So there's a bunch of things just in the acronym alone. There's a double asteroid, so we need to talk about that. Redirection, we need to talk about that. And then test. We need to talk about all of the words here, but one thing at a time. It's just been launched, 24th.
Yep, and it's going to go collide with an asteroid, basically to see can we change its orbit.
Right. So we're not sending a spacecraft up in order to try to land on it and plant a nuclear weapon on it. And who was the actor in that film? I'm trying to think.
Ben Affleck.
Ben Affleck, and wasn't there another one with Bruce Willis or something? I'm pretty sure Bruce Willis saved the world.
There's Deep Impact, isn't there?
Because there was Deep Impact in Armageddon. Anyway, Ben Affleck and or Bruce Willis. We're not doing that. We're actually gonna hit this thing. We're gonna bash a spacecraft on purpose into an asteroid.
Yeah, it's just like cosmic pool, right?
Yeah, okay. I mean, but it's not the sort of thing that we normally do with spacecraft, Emily. Not at least. Not on purpose. Like, there have been times in the past where we've tried to, for example, land on Mars. And instead what we've done is bumped into Mars really hard. Bit too hard. But that wasn't intentional. That was accidental. And all the astronomers and spacecraft people at NASA got really upset about that. This time, it's on purpose.
It's on purpose.
This is by design.
This is the design, I guess the whole scientific mission is based around, can we have a go at testing if basically what happens when we crash a spacecraft into an asteroid, and does it work if we try and divert it, and are our calculations correct on what we think should be the resultant orbit of this asteroid?
Okay, so let's pull back for just because, again, there's so many things here. Number one, we're trying to bash into an asteroid in order to divert it. What do you mean? Why would we do that?
So this is it's a binary pair of asteroids, or at least an asteroid and a moon system. Depends which way you look at it.
Can asteroids have moons? Is that allowed?
Yeah, it's allowed. Yeah, I guess it just sort of depends when's a moon and when's a binary is more the question. But anyway,
we did talk about this a little while ago. It's got something to do with center of masses. Let's move on.
Yeah.
Two asteroids.
Anyway, there's two asteroids. Now these two asteroids are in no way anywhere near the Earth. They are not going to come very near the Earth at all. And so they were just chosen, well, particularly for this purpose. So if everything goes wrong, they're not going to come and crash into the Earth.
Right. So this is not, hey, get the president on the line. We've discovered a major problem. Quick, send something up in order to save the planet. It's, let's see what would happen if we did this with a view to the future of, in case we need to put a phone call through to the president.
Yeah, exactly.
Okay.
Yeah, so this is our test. So these two asteroids, we got Didymos and Dimorphos.
Didymos and Dimorphos.
Yeah.
Good names.
Greek names.
Yeah. Dimorphos meaning two shapes, two forms,
yeah.
something. Yeah.
So the idea with Dimorphos, the name, is that the orbit's going to change.
That's the one we're bumping into.
Yeah.
Right.
So we're going to change its name, which is why it's called Dimorphos. Didymos means twin.
Right.
Yeah.
Okay.
So
well, that kind of makes sense then. So why are we, like it's in the name, right? Double asteroid. Why have we chosen this system? Why wouldn't you just go and bash into an asteroid?
So if you just went and chose, so asteroids are, let's go back all the way to what actually an asteroid is, because this is probably quite a useful place to start. So an asteroid is kind of a chunk of rock that is orbiting the sun at some point. Now, of course, made famous by the asteroid belt.
Yes, of Star Wars fame. And we know that asteroids have very large sort of sock puppet lizards in them that try to eat spacecraft. We know that.
Yeah.
Come on, I've seen the film.
So, in our solar system at least, the asteroid belt is this kind of area between Mars and Jupiter where a lot of asteroids hang out.
Yeah.
We're not talking about the asteroid belt.
Okay.
Asteroids live other places in the solar system.
Right, other asteroids are available.
Yeah. Because, that's quite a way away between Mars and Jupiter. So instead what we're looking for is more nearby asteroids. They still orbit the sun, but they're usually on pretty freaky orbits. So they're not kind of nice little well-behaved circles like the orbits of the planets. They can be quite eccentric, so quite elongated orbits. They're usually not in the plane of the orbits of the planets. And they can vary in distance, therefore, from the sun.
Right. Okay. So we're not heading out to the asteroid belt, which like lots of asteroids, presumably the leftovers of planet that got bashed or didn't quite form or something.
Yeah, a few ideas why the asteroid belt might be there, but
But we're not going there.
Stuff.
We're not going there. So where is this double asteroid system?
Well, it's just kind of just in space. I don't know how else you describe it.
Is it? You said it's not as far away.
No. So when we collide with it, it's at about 11 million kilometers away.
Give me something to hang on to there.
So we're about 150 million away from the sun.
Mm-hmm.
So
10%
ish the distance, but
sure.
less than.
In what direction? Sort of up, away, towards Mars, sort of up out of the plane?
In space.
Okay, in space. Fair enough. I will give up on this line of questioning. We're in space, and there's a double asteroid system, and we're going there. Is it just hanging out by itself, or is there a bunch of asteroids around there? Is it just...
It's just on it. Well, as far as we know, it's just on this orbit.
Okay.
So orbiting the sun. So Didymos is the one that's orbiting the sun, and then Dimorphos is its little moon that's orbiting it.
Right. And we just know it's there. We happen to have seen it. How big are these things? Do we know?
So Didymos is estimated to be about 780 meters wide.
And that's the bigger of the two?
That's the bigger one.
780 meters.
Yeah.
Okay.
And Dimorphos is about 160 meters wide.
I'm still amazed that we can actually see these things. I know astronomy's good, but like if you're pointing your telescopes in the direction of a large number of asteroids that you know are there, like the asteroid belt, then I can kind of see how, so, zoom in on that a bit and focus a bit and all of that. And we can see things. But this is just in space. Like, how do you see that? How do you know that that's there?
When I show you the pictures of these things, which are our best pictures, you might be kind of a bit more understanding and a bit less impressed that we have seen them.
Okay.
They are just kind of little fuzzy blobs.
Even so, though,
yeah.
like, did we just happen to spot one of these things?
Yes. Well, in 2003, we discovered this, at least the larger of the two in the system. I think both of them at the same time, actually. We're searching for these things all the time. We're actively looking, scouring the skies for these objects. So at the time they were discovered, they were actually a little bit closer. They're about 6.5 million kilometers away. So we're a bit brighter, a bit easier to spot.
I don't know. I'm just staggered that we can see it at all. But okay, let's park that for a moment. It's there.
Yep.
They're there, orbiting around each other. Cool. So we're going to send something out and bash into the smaller of those two. But why? Why do we need a binary system? Why not just find an asteroid?
Yeah, so that's we're coming back to that question. So if you look at say your typical asteroid, which is orbiting the sun, it will be on orbits that are, if not hundreds of days, then years long, right? And so if you smash into it with something, it's going to change its orbit by a little bit. But how do you measure that? I mean, it's really hard.
Right. So you can bash into something. And the idea here is not that we're going to try to bash into it and destroy it. We're not going to try to land on it and plant a nuclear weapon on it. We're not going to bash into it and try to break it apart. We're just trying to nudge it. That's the idea.
Yeah.
And that's presumably important because in this future scenario where there's one coming towards us and we have to call the president, then if we get it far enough away and we can give it a little nudge, that's maybe the difference between global catastrophe and it whooshing past at a safe distance. If we get far enough away and give it a little nudge, we're safe.
Yep.
And so the idea here is, well, let's bash into it and give it a little nudge. But then you've got to measure that and figure out what you've done.
Yeah, exactly. So it's much easier to do that with this kind of binary system where you've got the moon. Okay, first of all, it's a smaller asteroid. It's more of the size that we kind of might expect to be in our kind of, a big asteroids we can spot because they're bigger and brighter. So even though they're more dangerous to hit the Earth, they're very unlikely to, and they're easier to find.
Right. You'd see that one coming from much further away and presumably try to do something about it. But the smaller ones are scary.
Yeah, this kind of like 150 meters sort of size is kind of where we're trying to find them all, but we haven't found them all yet. And so we might be finding things fairly late on in the piece.
Okay. So this is a test. That's the last part of the acronym of a double asteroid. What was the R? Double asteroid redirection test. Okay, so we're going to try to redirect the smaller of these two. And so we're not trying to knock the little moon asteroid out of its orbit. We're not trying to obliterate it. How big a difference are we trying to make then? What's the nudge?
Well, you might be surprised. It's not much at all. So we're going to smack into this 160 meter wide thing with a spacecraft that weighs maybe half a ton. So kind of a small car. Yeah. Really small car, actually.
Small car hitting 150-ish meter wide chunk of rock.
Yeah.
It's kind of like, it's not quite ping pong ball against truck, but it's not far off.
It's not a lot. So its current orbit, we think, is around 11.9 hours long.
11.9, okay.
And the intention is to change this orbit by something like 73 seconds.
Okay, so that's quite a small nudge then. This is really not, like, the asteroid's not even really going to notice it much. It's just going to be a poof, and then, what was that?
Yeah.
Bug against the windscreen style. And yet enough to give it a bit of a nudge, to change its orbit.
Yep.
Wow. Okay. That doesn't seem like much, though. Is that of the order of what we might hope if we had to do something in a real hurry? Or are we just at the very early stages of, let's just try something small?
Well, actually, you don't need to move things a lot. If two things are on a collision course in the solar system, the solar system's got a lot of space in it, right? It's quite a lot of empty.
As we keep uncovering in this podcast, space is big and it's not got much in it. Yeah.
No, so actually, if you think about the Earth's orbit around the sun, we move around the sun at what? I think it's something like 30 kilometers every second.
Okay. Yep.
That we move. So if you think about the whole radius of the Earth, so whole diameter of the Earth, then we actually move a whole Earth diameter. I think it works out to be about 7 minutes.
Yeah, I can go with that.
So, I mean, all you've got to do is delay an asteroid by 7 minutes, and then we're completely gone. We're not even there anymore, where we should have been to
Could have been the end of the world, and instead it's just, whew, that was close.
Yeah. So it's not much, really, that you've got to change these things by.
Yeah. Okay. So you don't need to bash into a large chunk of rock with an equivalent sized chunk of rock, billiard balls style, in order to send it careening off in a completely different direction. You've just got to give it a nudge. Yeah. Okay. So how big did you say this spacecraft. How big is DART?
So, well, by the time it hits it's about 600 sort of kilos when it smashes in. It's going to be about 500 kilos.
And is it hitting head on? Is it hitting from the side? Like, how do you do this?
I think it's supposed to sort of try and get a kind of fairly head-on collision. So we remember when we talked about Rosetta? Do you remember Rosetta, our little comet mission?
Oh, but that was the one that sort of landed on the comet.
Yeah, Philae landed on the comet. Yeah.
It sent down the little Philae. Yeah.
Yeah, and the kind of analogy that went around was basically we were landing a washing machine on a comet because that was about the sort of size of Philae.
Yeah. Okay.
So I guess size-wise, this DART is a little bit bigger. It's about 2 meters cubed. So, it's small box room size.
Yeah. And what did you say? It was about a ton or half a ton?
About half a ton.
Half a ton. Bashing into this thing presumably at great speed.
Well, we anticipate it's going to be hitting at something like 6.6 kilometers per second.
Okay, that sounds fast. What's that in real money? In kilometers an hour? That's 6.6 times 60 times 60. Do a quick calculation. 24,000 kilometers an hour? That's fast.
It'd be nice if you could travel that fast.
That's very fast, even for a relatively small chunk of metal against a very, very large chunk of rock. That's carrying a significant amount of energy. So it's going to change its orbit by subtly small amounts. Cool.
Yeah. And if you're doing kind of, I guess, what GCSE physics and above, you'll be able to do the calculation and see, because you've got, all it is a very straightforward transfer of momentum.
Yeah.
Momentum's conserved.
Yeah. And so figure out what that does to the orbit of a chunk of rock. Speaking of which, you said to me a minute ago, I wouldn't be terribly impressed by the pictures that we have of this thing because they're a bit fuzzy, right? We're now going to go and bash into a relatively small lump of rock at high speed with a piece of fairly expensive equipment. Can we see this thing well enough to actually then measure what's happened? Like, that's the bit I don't get, is how do you've just destroyed your spacecraft. How are you supposed to know what's happened there?
Well, and this is where the brilliant thing comes in, because of course DART has got its own personal photographer on board.
Presumably, which will not be on board.
No, won't be on board when it crashes.
Time.
No, so this is like, I'm going to go with Lycia cube.
Okay, Lycia cube.
Okay, Lycia is
how do you spell it?
Lycia is a brilliant acronym. Well, I'll tell you what it stands for first, because I think that gives you some hints to the pronunciation. It's the Light Italian CubeSat for imaging of asteroids.
Nice. Okay, yeah, let's go with Lycia. Lycia cubed.
Yeah. So this is going to be a little CubeSat sort of thing, which is going to be released about 10 days before impact.
Oh, okay, so it's on board.
Yeah. So it just pops off about 10 days beforehand and then continues, flybys the asteroid.
just follows it in. It's like, no, you go and do your job and I'll just take pictures. Wow.
Yeah.
Cool.
So it's going to go take photographs of the impact site, anticipating a crater of maybe 10 meters in size.
That's what used to be. What used to be DART. Okay, cool.
So
it's going to be taking the data and presumably taking data of like that we can then figure out the change in the orbit. Like that's...
Yeah, a little bit. I'm not sure exactly how many sensors. These are quite simplistic spacecraft.
Right.
I mean, when you've got kind of disposable mission, you don't want to spend a lot of money on instrumentation, I guess.
Fair enough.
But there is going to be Hera, which is an ESA mission that will go past in about 2026.
Right.
It's also going to take some pictures. So we've got a kind of more, I guess, big brother follow-up later on.
Okay, but the point is that I'm inferring from this then that we can actually see this system well enough to be able to accurately measure its orbital speed, like its orbit, accurately enough to be able to tell that we've made a difference.
Yeah.
Right.
And we'll be able to refine all the measurements, of course, just before impact as well. So if our fuzzy pictures weren't quite exactly what we were expecting when we get there, then there's some opportunity to slightly adjust, right?
Very cool. Okay. So this thing launched just a couple of days ago. So in real time, that was, what did we say, the 24th of November? Okay. Yep. So how long does it take to get there?
Just under a year.
Under a year. Okay.
Yeah.
So roughly this time next year, do we get to have a viewing party? Like, is the CubeSat sending back high resolution video for us to be able to watch
I think it's going to take a little while to come in, but potentially around about the 26th of September, I think, is the optimal date. But it could drift a little bit into October, depending on what's going on.
Right, but not necessarily with the YouTube live stream.
No. We're going to be getting pictures, but we remember getting like pictures from the surface of Mars from these kind of things.
Yeah.
It takes a while to
I don't know. I mean,
through.
that would be cool to be able to live stream it, but I can understand how maybe that wasn't within their mission parameters and budget.
Yeah.
Cool. Okay, so in roughly a year, and then presumably there's a whole bunch of analysis to do.
Yep.
To then figure out, so did that work? Did we hit it? Did we miss it completely and just sort of head off into outer space? I mean, 24,000 kilometers an hour is very fast.
Yeah.
And it's a very small target. Is there a chance that they're actually going to miss it entirely?
I hope not, because again, as I say,
they all hope not.
You can do tiny corrections as you go if you really, really need to.
I don't know. It kind of feels like that's a really small target. Whang, there it goes. Oh, we missed it. Bring it back. No, it's too late.
Yeah, but you think about some of the missions we've done in the outer solar system, right? We've managed to intercept with Pluto. And, okay, Pluto's a bit bigger.
Bigger than that.
But you think about the number of years that you had to wait between, say, New Horizons. It was, more than 10 years, I think it was, that you had to wait. So you had to plan your pit stops along the solar system kind of 10 years in advance of when you were going to get there.
I guess, the people involved in working this stuff out really know what they're doing, and I'm prepared to give them all of that benefit of the doubt. I just kind of feel like a 150-meter wide target and 24,000 kilometers an hour, like those two things just don't fit in my mind. Like I can't imagine me doing it, so I don't know why anyone else would be able to. That's a really stupid thing to say, and I'm going to retract that now. Let's assume that all of the space people know what they're doing, shall we?
Yeah.
Okay, so roughly a year or so's time. Look out for an impact on an asteroid somewhere, hopefully not too near you. So that then does kind of bring us to, let's assume that all goes well, right? How big a deal is this? Should we sort of broaden out now and sort of ask the question, is this a problem that we ought to worry about and spend a lot of money on?
It's a good question. In some ways, it's a very difficult question to answer because you can go to two extremes on this. So asteroid impacts onto the Earth happen all the time. And as I think almost every astronomer will tell you, if you're talking about sort of catastrophic events, it's always just a matter of when, not if.
Yeah, I mean, these things have happened. It has happened. And depending on your definition of catastrophic, I mean, within a lifespan, there have been, what was the one in Siberia? Was it the Tunguska event or something? Mm-hmm. Which had, this was an explosion, I think it was a meteor, because it didn't hit the ground, so it's not a meteorite. Is that right? Have I got that right? A meteor which exploded in the atmosphere over Russia, somewhere, over Siberia, and flattened trees in 100-kilometer radius or something. It was massive, absolutely massive. And if that had happened anywhere near an urban area, then that would have been extraordinarily bad for anyone nearby. Turns out it wasn't anywhere near people. And so it was sort of a bit of a mystery for a while, with a bunch of people turning up going, why are all these trees fallen down for a very large area? But that could have been really, really bad. But presumably that sort of thing is happening reasonably regularly. And then, of course, the big one that everyone knows about is the dinosaur one.
Yeah, exactly. Yeah.
Which wiped out most of the big things on Earth. So how often would we expect?
Well, it's interesting. So let's start small, right?
That's a good place to start, sure.
Earth is sort of turning along on its merry little dance around the sun in space, right? Along the way, as we go around our orbit, we pick up something like 100 tons a day of dust and kind of sand grain size particles that are just kind of kicking around in our orbit. Right,
we're just collecting it as we go.
Yeah,
sure.
100 tons is a lot, though.
That's quite a lot, but I mean, the Earth's big. So, it's, it's a lot, but in small bits, small chunks.
Exactly. So you never see them. You don't notice them. They burn up instantly in the atmosphere. It's fine. Right.
Okay.
About once a year, we get something kind of about the size of a car. So you've probably seen several times over the last few years these big fireballs in the sky.
Yeah,
that people see.
yeah. The ubiquity of dashboard cameras seems to have made that a viral phenomenon, that every once in a while you'll see this video go viral of someone's dashboard cam in, Switzerland or something, middle of nowhere. There's this fireball going across the sky. And just because we've got cameras everywhere now that we see them, and it's really cool. Yeah, and that seems about right, once a year.
Yeah, so something about the size of a car. Now, they're all going to burn up before they reach the ground. In fact, anything that's smaller than about 25 meters in diameter is going to completely burn up. And that's not to say it doesn't do damage, because these things are quite explosive. Even in recent years, we've had fireballs that have broken windows, that kind of thing.
Yeah, the big shockwave that comes when the thing presumably gets so hot that it explodes.
Yeah.
That it just, boils and explodes. And that sends a shockwave out through the atmosphere that breaks windows. And
so they do a
scares
bit
dogs
of
and stuff.
damage,
Yeah.
but kind of very low level, really.
Hey, when you go out on a really clear night and you see a shooting star, right? Like, how big does it have to be before you see it?
It's a good question. They're actually usually quite small. I think they're usually kind of around about 0.5 meter to 1 meter, that sort of scale of size.
So you'd never see, or you said before about all the several tons of dust that we're picking up every day, and that's really, really small, and you'd never see that.
Yeah.
And then there's the sort of, up to, what did you say, up to 25 meters. They're the big ones.
Yeah.
And then in between that is the stuff that you would see on a clear night, just every common or garden shooting star.
Smaller than a car at least, because those are
car.
those fireball ones that you really take notice of.
Okay.
Yeah. So that's kind of okay. But then once about every 2,000 years, roughly, then you'll get something maybe about the size of a football field.
That's starting to sound disturbingly large. Yeah. And is that kind of your Tunguska blast of 1908 style?
I think yes-ish, but I don't think they think that one got to the ground, which was interesting. I think that one sort of fragmented itself.
So maybe that wasn't quite that big, but it was still big enough.
Yeah, it was still big enough, yeah.
Yeah, that'll do.
Yeah, so anything from kind of football field up to 1 kilometer in size, you're looking at kind of localized damage. So, yeah, of course, buildings, windows, cars, if you're in the wrong place at the wrong time, fatalities.
You don't want to be near that one.
Yeah. So they're kind of dangerous, but, we live in a world which has a lot of natural disasters in it.
Sure.
So it's kind of comparable to the small scale natural disasters, I think.
And so, sorry, you said sort of football pitch size. Is that the size when it hits the ground, or is that the size
we're talking about all these sizes are sizes when they enter the atmosphere.
Right, okay.
So they do burn up and become smaller, but you need to be 25 meters to begin with before you have a solid object that hits the ground. Right. If you're lucky and you stay in one piece, basically. If you fall apart and break into things that are smaller than that, then the little bits will burn up themselves.
Okay, so football pitch size thing hitting the atmosphere roughly, let's say, once every couple of thousand years.
Yeah.
Sure.
So then we got to something like the size of 2 kilometers in diameter.
This is starting to sound very nasty.
Starting to get a bit bigger. Yeah, this is when we're talking about worldwide effects of an impact. Now, these are very rare, so probably only once every few million years.
So is this the dinosaur-sized thing, or are we not even that big yet?
Well, the dinosaur was 10 kilometres maybe wide.
Ow.
So that was on the big end of this scale.
So do we have any record of something on the scale that you're talking about, like small? Has there been anything since? Like everyone knows about the dinosaur one, right? And it kind of feels like there was the dinosaurs and then nothing to speak of. Has there been a big one since?
I can't tell you when, but there's
Why is that
kind
a
of
secret?
Well, no, I just don't know.
Sworn to secrecy.
But there's a few places in the world you can go and see these big impact craters, right?
Yeah.
I know there's one in Arizona, I think.
Yeah, which really does look like a special effects, you know. If we had to draw a big crater in the desert, what would it look like? It looks like that.
Yeah.
That's a real thing.
And look how it just missed the visitor centre kind of thing.
Yeah, exactly. What are the odds? Yeah. And I think I want to say there's a similar one actually in outback Australia, but I could be wrong. I'd have to look that up.
There's a few of those kind of scale ones. So they're around this kind of kilometre sort of size. I don't know when those particular ones fell, but whether they were before or after dinosaurs, maybe.
Sure. Okay.
But let's go with, kind of not in the too horrifically distant past. Otherwise, they would have been eroded by Earth's like water,
Yeah.
ice.
Yeah. And those, I mean, that crater, the one in the US, I mean, not only is it stunning to look at because it's wow, like something really happened there, but it's very big. You know, that would have made a lot of noise and a lot of light and a lot of raining down from the skies of terror and destruction. That couldn't have been fun to be near.
No, and what the problem with these big impacts is you get a lot of dust that goes into the atmosphere, and that actually makes the whole atmosphere of the Earth kind of actually a little bit more reflective to the sun's light. So you actually cool down the Earth because of that. Yeah. So yeah, that's why you have these global effects.
Yeah. Well, and that was the big problem for the dinosaurs, wasn't it? It wasn't so much. I mean, you know, if you were a dinosaur underneath the thing when it hit, then yeah, totally, that would be really, really bad. Or indeed anywhere near. But even on the other side of the planet, all the dinosaurs got wiped out, and a lot of other animals too, because suddenly the entire food chain was disrupted because the sun went out, because the entire planet was covered in stuff from the impact, and the whole food chain just collapsed, and all the dinosaurs went, I've got nothing to eat, and died. Yeah, which is kind of sad.
Yeah.
Yeah, okay, but fortunately that's not happening terribly often.
No. Once every few million years for at least the smaller scale. Remember, the dinosaurs is the bigger end of that. But, so, those are just like rough estimates, right? There's nothing to say that once every few million years is going to not be next week.
Yeah, I mean, that's the weird thing about stats, right? Is that all you can do is pick up a whole bunch of when did this happen, when did this happen, when did this happen. So on average, when would we expect the next one to be? And you get this range, which is from like now through to maybe a couple of million years in the future. And it could literally be tomorrow, which is sobering. So what does that mean? What do we do about that?
Well, I mean, the good news is we're pretty good at looking for at least the largest scale of objects. So this has been recognized as a threat to humanity for an incredibly long time. I think even Stephen Hawking wrote about it, saying this is the biggest threat that humans ever will face is an asteroid impact.
Wow. And I mean, Hawking was a dude who thought a lot.
Yeah.
You know? And so I guess you'd kind of take that seriously from someone who spends a lot of time in their own head thinking about big things is, yeah, maybe we should look into that. So when did we as a species first really start taking this seriously from a sort of astronomical point of view and start looking?
I guess ages. I mean, this is not a new science, right? People have been worried about asteroid impacts, I guess, forever.
For as long as we've known that that's a problem,
should
we start looking for these things?
Yeah, but the problem has been, I guess, up until, the last 50, 60, 70 years has been just technology, right? How do you spot these things? They're very small. They don't have any light of their own, so that all you're reliant on is the reflection of the light from the sun, and even that's got to be angled at the right kind of way for you to see it, because if they're between you and the sun, that's much harder. I mean,
when you consider it's only, it's within the last 100 years that we've only been able to piece together some of what now seem to be fairly obvious parts of the sort of cosmic jigsaw puzzle, like galaxies, that we're in one and there are others, that kind of level of things. It's maybe not surprising that our ability to be able to spot tiny little lumps of rock coming our way is fairly recent. Yeah.
So we've been working on this for a while. We've got lots of projects going. It's interesting because there's kind of a diverse interest in looking out for these things, what we call near-Earth objects. So the ones we're most concerned about are basically things that are going to come closer than the moon. That's kind of a rough scale. If it's not going to come closer than the moon, we're probably all right.
I mean, the moon is a very long way away in terms of Earth diameters and so on. Like it's further than you think. And yet, I don't know, any large chunk of rock coming closer than where the moon is does tend to make you sweat a bit. So
yeah, but it happens all the time, actually. In 2020,
just last year,
about 107 objects came between, what would have been equivalent between us and the moon's orbit.
When you say objects, like what counts as an object in that count?
Yeah, so things that are proper trackable asteroids that could have impacted us.
Which translates as a decent chunk of rock.
Yeah.
Something that could have hurt.
Yeah.
Right.
At least a little bit.
How many?
107.
Right. Okay. I mean, again, it is a large space, right? It's a big radius sphere, or I guess target circle that those things can pass through. But that's quite a few just in 1 year. That does tend to make one a bit nervous.
Yeah. But we've been looking for a long time for these objects. Now, there was a big project. As I say, there's quite diverse interests. So there's things like the astronomical kind of space sector, who obviously don't want these things to crash into our space telescopes and international space stations and things like that.
Yeah.
So we care about that. So the likes of NASA care. There's actually defense, military defense of different nations care about this, and private individuals and businesses, and particularly now that we're entering the era of much more commercialization of space, there's a bit more commercial
need to look
business.
after our commercial interests.
Yeah. So it's interesting.
Not to mention, the continuation of our species and every other species on the face of the earth. But, yes, commercial interests, sure.
So historically, most of these things have been led by sort of astronomical programs, and NASA's been a massive part of that. And one of the first big goals that was run, I can't remember the time frame off the top of my head, but it was kind of, I guess, in the last sort of 30 years or so. They were trying to find about 90% of the objects that were bigger than a kilometre in size that might impact the Earth. That was their mission from all these surveys. And they were successful. And so we've got that. So we know that basically there's nothing that we know of that's of that kind of size, kilometre or bigger, that's going to on a collision course for the Earth.
Okay, good.
Yeah.
That's, good.
It's good. And in fact, the largest known thing that's sort of not even going to come that close is about 5.5 kilometres in size.
So that would hurt, but on the other hand, it's not coming our way.
No.
So that's good.
No.
How sure are we of this?
Well, we're talking about, again, 90%. There might be
Right.
a few odd bits and pieces out there, but we've got a pretty good handle. And if we come to now the current day, I sort of tried to do a quick kind of summary of what are the major projects that are now looking for these near-Earth objects, because even I know astronomers who work in this, who look at, use big telescopes to try and to track down these things and try and characterize their orbits. And honestly, there's heaps. There's really quite a lot. I didn't even write them all down in the end because I got kind of to the point of like, whoa,
There's
this
a
is
lot going on.
This is getting overwhelming. Probably one of the biggest ones is a project called Linear, which is the Lincoln Near-Earth Asteroid Reconnaissance, I want to say. I didn't actually write down what the R was. Research maybe, actually. And that's kind of a big project that's got funding from NASA and many others. And there's this kind of, I should have started with this, there's this kind of collective group of projects all around the world, run by different organizations, some of them national government, military, etc., some of them astronomy, some of them business, called Safeguard.
Is that
Spaceguard, sorry.
Spaceguard.
Spaceguard.
Is that an acronym or is it just a cool name?
No, it's just something they decided to call it Spaceguard.
Spaceguard. Better than Space Force. I'll give it that. Spaceguard.
Yeah, it doesn't quite sound real though, does it?
No, it doesn't, but that's okay. I mean,
Yeah.
if you're gonna have a big collaboration looking for big chunks of rock that could kill us, then Spaceguard's not bad.
Yeah, I think it's a very loose collaboration.
Right.
I think the only thing that makes them a collaboration is they're all trying to do the same thing.
Okay, right.
And some of them talk to them a little bit more than others. But yeah, then you got things like Linear, you've got astronomical surveys like the Catalina Sky Survey, which is very famous. Pan-STARRS is another big sky survey that's going on looking for these things.
And are they all trying to do the same thing, which is we're trying to spot chunks of rock that could come and hurt our stuff and ourselves? Or are there other aspects to it? Like, are there other reasons to find near-Earth objects?
Yeah, I mean, they're interesting in their own right.
Sure. Look, I mean, astronomers can find anything interesting in space. So,
well, like asteroids are sort of relics from the formation history of the universe.
Right.
So, solar system at least. So, yeah, we are interested in these. So these are the more sort of astronomical bent projects. There are some that are set up explicitly as alert systems. So ATLAS is one, which stands for Asteroid Terrestrial Impact Last Alert System.
Can we have the first alert system? I'd rather that one. I don't like anything that says last. That's the one that says the big red warning light's gone off. Head for the bunkers or not, because it's not going to help. You know, That's what that says to me.
Well, yeah, and that's true. But when you think about what their mission is, they're looking at the small stuff. So they're looking at things that are only kind of down to 10 meters in diameter. So these are the kind of fireballs that might cause localized damage. So they're trying to kind of, if we spot them just before they come, maybe we can get some, very quick warnings out.
Right. Well, I mean, my suggestion to the Atlas people is just maybe have a little bit of a think about softening that name a bit. It just, you don't want to frighten the horses.
So then you got ESA one, there's NeoShield is one that's looking really at detection and characterization of these objects, because even if we do want to smash objects like dart into asteroids, kind of helps to know what they're made of.
I guess.
To know what's going to happen. Are they just going to fall apart? Are they going to stay together? All these kind of questions.
Yeah, I mean, it would really suck to bash into something and then realize, okay, so now we've got 3 pieces coming towards us, all of which can kill us. That didn't work terribly well at all. So, yeah.
And the final one that tickled me a little bit was one called Sentinel. I think I've even heard of Sentinel before.
Sentinel.
So Sentinel is a private non-profit foundation. Their original idea was to build a space telescope and put it in near the orbit of Venus and just look back at Earth and say, is there anything heading your way?
Sounds good. Also sounds expensive and difficult.
Yeah. So they did have some funding
Is
from
this
NASA.
just an excuse to get a cool space telescope?
Well...
And it could save the world.
Ended up not really being funded that well.
Ah.
So they've maybe kind of changed tack and are looking at maybe constellation of CubeSats or something.
Right.
But it seems to have gone a bit quiet.
Not quite the same. Still, chutzpah for, for giving it a shot, I reckon.
Anyway, the upshot of all this is that we now know of about 27,000 asteroids which may come close to Earth.
Right. Okay. But still none so far that we've got the big flashing red light on going, by the way, in a decade's time, we're in trouble.
Well, some of these are more certain than others, right? We must consider the error bars.
Yeah, in science, everything that we measure has a certain uncertainty about it. And when you're measuring something in the lab, that's not life-threatening necessarily. But if you're measuring a large chunk of rock coming towards the Earth, it's going to miss within error bars, start sounding a bit iffy. So,
well, these things are really hard to track sometimes, and sometimes we can get of the larger objects that are kind of in the right place with the right illumination, and we can get radar and all this kind of stuff. That's fine. We can get really good orbits for them, but some of them are tricky, and so there is an amount of uncertainty. That's why it's kind of may come close.
Right. Is part? I just had a sudden thought. Is any part of the problem that if something's coming towards us, it's not moving across the sky terribly much. It's just getting a bit bigger. Like that asteroid there, it doesn't seem to be moving. It's just getting bigger. Oh, quick, call the president.
I think
probably doesn't work that way, does it?
Not quite, because we're moving.
Yeah. Still, it's a nice mental image.
But the good news is we don't know of anything that's larger than 140 meters.
Okay. I mean, that would still mess you up a bit, but it's not as bad as it might be.
Yeah.
Yeah.
Not knowing anything bigger than 140 meters that's going to hit us in the next 100 years.
Well, that's good. That's
good
good.
News.
Presumably by 100 years' time, we'll have like massive orbiting space lasers to blast them away anyway. So, Elon Musk will have his he'll be living forever by that point, and he'll have his space lasers to protect us all, and it'll be fine.
But we think we've only found maybe about 40% of them.
Right. Okay, so hang on, winding back a little bit, you said that we had something like 20-something thousand that we've catalogued so far, and we're fairly sure, to within error bars, that there's not terribly much coming our way, but that's only 40%. We reckon that's only 40% of what might be out there. Is that what you're saying?
At least of the ones that are bigger than this 140 meters.
Okay. I've done a bit of maths. That leaves 60%. That's on the wrong side of the sort of 50-50 barrier, Emily.
Yeah.
That leaves a lot. Like, forget about the error bars for a second. That's a bit like the whole dark matter, dark energy of the universe thing. Well, we know about the matter part. Yeah, that's fine. That's 5%. Like we know about 40% of the chunks of rocks that could kill us. We just don't know about the 60% that we don't know about. Isn't that a problem?
Well, I guess that's what we're trying, right? We're trying with these surveys to find
It's not a
them.
criticism. I'm just saying this whole conversation makes me a bit nervous. That's all.
And if nothing else, it means that maybe we should think about, hey, if we do find something, what are we going to do about it?
Yeah.
Because I think there's quite a famous conversation that was held in the US Congress a few years ago, which was basically, if there's something coming towards us, can we do anything about it? And the short answer was, well, no, because it would take us about 4 to 5 years to develop any kind of spacecraft that could do it.
Yeah. I mean, we're not going to be relying on sort of Dart 2, because Dart 1 is tiny and wasn't designed to save the world. We can't just build another one of those. So, yeah, okay. Well, let's hope that there isn't anything really nasty in that 60% coming our way anytime soon.
Yeah, but
because we know that drill, right? We know that it's going to be the president and all of the other rich and famous and powerful people heading for those underground bunkers, and or the big boats that are going to somehow stay afloat. Anyway, they're all going to be safe. They're all going to be fine, and the rest of us will be just, trying to get through the barbed wire fences. Yeah. We know how this works.
So this, I guess, the summary is, it might happen. Yeah. We're not exactly prepared for it, but we're taking some steps in that direction.
Right.
And we've actually spent a long time thinking about how can we change and say, how can we get rid of a potential threat? So I guess this is the fun part now.
Yeah.
So there's loads of ways that you could potentially get an asteroid impact kind of just not happen.
All right. So let's say, for the sake of an argument, that an astronomical team, one of these collaborations, has looked up and gone, funny thing, we've actually found one of the 60% and we have a problem. All right, Emily, over to you lot. Solve the problem. What are we going to do?
Well, I guess there's two basic things you can do.
Yep.
You can go for basically delay. So this is exactly what DART's doing, for example. Change the orbit so that the impact is no longer going to happen and we all continue on our merry way.
Just give it a nudge. Doesn't have to be a huge nudge, just a nudge.
Yeah.
Yeah.
Well, nudging is one way to do that delay, but yeah, there's a couple of others. But basically change something so they're no longer going to hit each other. The other option, which is perhaps the more dramatic one, is called fragmentation.
Blow it out of the sky. How do you do that?
How do you think the first way that you could possibly get rid of an asteroid through fragmentation would be?
Big bombs. Lots of explosives.
The first thing you'd think about would be to nuke it, right?
Yeah. Surely there are already rockets armed with very, very large amounts of nuclear weapons somewhere in a bunker, probably in Arizona, ready to go and do it. And someone's just, give me an excuse, let me hit the button, because someone wants to do that.
It just seems to be part of our culture, isn't it?
It
the
is.
First thing we would go to is
there's a threat coming our way. Nuke it. Really? Isn't there? Couldn't we do something else? Is there someone else I can talk to?
Yeah. So I mean, nuking it in a sense would probably work-ish.
Yeah.
I mean, what you're doing is you're sending. Okay, we need to put it on. We can't just do our surface to air missiles and so on that we have currently, right? It needs to be something a bit more purpose designed, go up in a big rocket to get it into space, put it on an orbit, blah,
presumably
blah, blah.
Go quite a long way, because you don't want to wait till the last minute. You got to go and meet this thing where it is.
So you can blow it up into smaller pieces. The good news is that will make it smaller.
Yeah.
It will probably also change the path of all the individual smaller pieces that it blows up into. You do have to be a little bit careful, because I was watching a documentary actually the other night about hurricanes. And so one idea is how to get rid of a hurricane is to stick some nukes into the middle of it.
Oh, yeah. I mean, I've read about that. And isn't it that the American, whichever research organization which is in charge of America's, climate stuff, they get they get this question all the time. So they've got on their webpage, can't we just nuke the hurricane? No, you can't just nuke. It doesn't work that way.
Well, in theory, it kind of would if you had a big enough nuke and you had... Anyway, but basically the upshot of 99.999 times out of 100, you're going to get just a radioactive hurricane.
Yay! That worked well. Let's put some sharks in it too. Let's go the whole hog.
So the same thing kind of goes a little bit for the nuking an asteroid. You've got to be a bit careful, because you might just end up with a radioactive asteroid, or at least chunks of radioactive asteroid heading towards you.
The good news Mrs. President, is that we did manage to destroy the asteroid. The bad news is that we now have 20 radioactive asteroids coming our way. Yeah, so that wouldn't be so good.
So you're going to make sure they're all little pieces and you've all moved. Probably that would
Yeah.
happen, but can you be sure?
Yeah.
Don't
I mean,
know.
couldn't you just combine the two? Like you've got the nudge technique and then you've got the nuke it technique. Couldn't you do a nuclear nudge? Couldn't you send a bomb up and just sort of explode it beside it and push it off in a different, like, wouldn't that be a good way? Rather than bashing into it to try to nudge it, couldn't you
I
push
guess
it away with a
sort
bomb?
of, yeah. And I guess you're coming a little bit to the, I guess what I would think of as a tugboat
Right.
technique. And this is not so much explode it away, but but like a tugboat, you take your spaceship, you attach it to it, and you just kind of push it.
Turn the engines up to 11 and we're going this way.
And so, like a tiny little tugboat can turn a huge container ship.
Over enough period of time. Yeah.
And actually, what's cool about tugboat sort of technique, I'm going to paint this if it's not already.
Yeah. I think this could be a big check idea. I like it.
Is that you actually don't even need to be in physical contact with the asteroid. You can actually orbit it and use the momentum exchange in the orbit to pull it out of
That's
out.
clever. That's physics, that is. I like
Cool.
that. Presumably you'd need a suitably big enough spacecraft to do that, though.
Well, ish. But remember, if it's this thing that's kind of, what we don't know what the mass is of this thing, but it's only 160 meters wide. You've got a kind of a 2, 3, 5 meter big spacecraft.
Over enough time.
You only need to pull it a little bit.
Lots of little nudges. Yeah, small tugboat, enormous boat. Yeah, okay. All right. Well, look, if no one's got that one, I think you should claim it. I think this could be the making of Brunsden Space Dynamics Incorporated. You could be the next Elon Musk. This could be awesome.
Exciting. Yeah, I don't want to had that responsibility though. Oh, sorry, we forgot to carry the 2 on that one.
Emily, we got the president on the line. Have you got everything sorted? No. Emily's not here right now. Sorry.
So the next one, this is a good name that I did see. The Ion Beam Shepherd.
That sounds good, if somewhat confusing. What is that?
So the thing with light, this is the crazy thing about light. Light has momentum. So the light that's raining down on us from the lights in my office, the light that's coming from the sun and raining down on us, it all has momentum. Every photon that hits you is actually imparting a little bit of that momentum into your skin.
Yeah, I mean, even though those photons don't have any mass, they don't have a rest mass, they can't be at rest anyway. They've got energy and they've got momentum, which is a weird thing about particle physics, but there we are. And there's a pressure, it hits you, you feel it.
So you can this ion beam shepherd, I guess you could use ions or you could use photons. Photons don't have a lot of momentum. So the idea is, well, maybe we could either sort of beam light onto an asteroid and actually push it using light.
Big
or
lasers, presumably.
exactly, giant lasers.
Yeah. So if you can't do nukes, do lasers. I mean, this is great. This is every mad
I feel
scientist's
like this
dream.
is not actually a scientific episode, is it?
Yeah, I guarantee you it'll have some of our highest ratings, though.
Yeah, so
Big lasers, yep.
Yeah, you can do it with big lasers, or this ion beam, which is you basically create ions. So these are charged particles. Charged particles are also kind of something you can control a little bit and kind of beam and direct,
Right.
Because they've got their charge and they will respond to a magnetic field.
Right.
So again, you take a spacecraft out with this big laser or a big ion beam, and you fire it at the asteroid and sort of push it.
I can totally see how this captures the imagination of a certain kind of slightly mad and very rich scientist / engineer. I bet there's a lot of money at the moment being pushed in these directions.
It's kind of fun, isn't it?
Yeah.
Equally, you could use focused solar energy. This was apart from the photon pressure, the momentum that you can get from that, there's an idea of this is true with lasers actually, and even the ion beams. If you ablate the surface a bit, then so you're actually kind of breaking stuff off the surface.
Ablating means, sorry, remind me.
Like breaking things off the surface of the asteroid. Of course, we've got Newton's law. Every action has an equal and opposite reaction. So if you kind of get things that are pushing off the surface, then it's going to push the asteroid in the other direction.
Right, yeah. If you start bashing or boiling or burning one side, then that's going to push it in the opposite direction.
Yeah.
Yeah. So what, like big big mirrors or big lenses?
Yeah, just giant. You know those solar cookers that you can get? Yeah. It's just like a big curved, shiny thing to focus sunlight.
This is the best episode ever. We've got nuclear explosions. We've got big lasers and what basically sounds like a Ghostbusters, proton pack or something. And then giant solar cookers to focus sunlight onto an asteroid. That's awesome. No, and now I'm going to guess here, Emily. None of these things exist, do they?
No.
These are all theoretical ideas that someone's come up with.
There is one that exists, which is DART, which is what we call a mass driver.
Right.
So that's just smash into it. And
watch
what happens.
Currently a one-off test flight to bash into a very small asteroid quite a long way away. Yeah. Still, I mean, it's something.
It's it's
not a giant space laser, but it's something.
Other mad harebrained schemes to change paths or to destroy asteroids are available.
Well, I mean, I think the point is they're not. Like, this is the only one we've got at the moment.
Yeah. Well, I mean, in terms of ideas, at least.
Yeah.
There's probably at least a dozen more mad ones, probably some which involve genetic engineered rabbits at some point as well.
I guarantee you there's one hell of a Wikipedia page about this. Yeah. Well, Emily, I'm not entirely sure how what started off as a perfectly sensible discussion of an actual space mission to do a test of impacting an asteroid quite a long way away, which is of no threat to anyone, just to see how much it would nudge it out of its orbit, turned into space lasers and solar cookers trying to destroy deathly asteroids. But here we are, there's no turning back. So thank you very much for bringing this all to my attention. I feel somewhere between terrified and mildly amused at all the different ideas that we've come up with. So thanks for that.
Well, if it makes you feel any better, so Carl Sagan, there's only been one, considered this problem as well and how you might sort of divert asteroids and how you would look at the technology, you might be able to do that.
I kind of feel like Carl Sagan would have been fairly sanguine about it, though. It's like, well, if this means the end of our species, then so be it.
Sort of, because I think his take on it was actually the most dangerous thing of all, is that if humans do develop the technology to divert asteroids and so on, what's the first thing we're going to do?
Oh, we're going to start firing them at each other, aren't we?
Yeah, of course we are.
Oh. I'd never even thought about that. Here's an idea. Let's find a way to save the world and then let's weaponize it. Oh, you're right. That's the first thing we'd do. Well, listen, let's back away from that one. Emily, if people wanted to get in touch with us with their harebrained idea that may involve actual hares or may not, genetically engineered rabbits, about how to save the world from impending doom by asteroid, how could they get in touch with their plans and schemes?
So they should definitely write to somebody else.
No, they should write to us because I want to hear about it. I think it'd be great fun.
No, we're on Twitter at SyzygyPod. That's SYZYGYPOD.
We have that name somewhere else as well.
We have it on Instagram. We have a thing where if you search Facebook, we come up.
Yeah, we still haven't got a good one for that. How do people talk about how they find you on Facebook? I think just search for us on Facebook. I think that's how that works.
Find it, click, or they can go to your website.
Yes, our website.
Absolutely. Yep, the beautiful, well, I call it yours because it's such a creative design masterpiece.
It is you're very kind. Syzygy.fm, where you can find all the past episodes, and a hello page where you can send us a message and say hi. As well as a page that lists all of our fabulous financial supporters who throw us $1 or £1 every episode or every month through patreon.com/SyzygyPod. There's that name again. But if you don't want to send us money in order to keep the electrons flowing through the website, you can support us in so many other ways. You can give us a review, give us some stars on your podcast chaser of choice, or you can just tell everyone you know that there's this fabulous thing called Syzygy where they talk about everything from the creation of galaxies and the beginning of the universe right through to stupid harebrained ideas about nuking and lasering asteroids. So spread the word and help us to rise up through the noise of the podcast universe. Anyway, that probably do us for this mad episode. Emily, I'll catch up with you in a week or so's time.
Yeah, I'm going to have to go read some scientific journals now to make myself feel better.
I think I'm going to go and have a little lie down. Catch you in a week's time.
Bye-bye.
Bye, everybody.